look at what's called physical optics. To start off, I just want to remind you of a couple things that we've learned before about waves. Remember that waves exhibit superposition, which means that their amplitudes just add whenever two waves meet. Okay, so if crest meets crest and trough meets trough, that means that there is constructive interference. And if crest meets trough and trough meets crest, that is destructive interference. Now, in order for light to interfere in a noticeable way, it has to be monochromatic, meaning all one color. Because if there are multiple different colors, there will be different frequencies, and so then the waves will be interfering, but superposition will be happening, but it'll be really hard to notice because there's just all sorts of different frequencies happening. So if they're monochromatic, that means they have the same frequency, and so they can have the same a constant phase relationship. And that's the other thing, is that they do have to have a constant phase relationship. So those two terms, they have to be monochromatic, one color, and then a constant phase relationship means that the term is coherent. So in order to have a noticeable interference pattern, they have to be monochromatic and coherent. All right. Typically, the lights that we use in classrooms and whatnot are not coherent, while lasers tend to be a good source of coherent and monochromatic light. All right. So you may also recall from when we talked about waves before that for two sources, in order to have constructive interference, you need the difference in path length between the two sources to be equal to some multiple of the wavelengths. Because if you're one wavelength away, then you'll have, if you're 0 wavelengths away, then of course you'll have crest meeting crest and trough meeting trough. If you're one wavelength away, the same thing happens. Right? And so this is the condition for constructive interference. And for destructive interference, this path length difference needs to be a multiple of half a wavelength. Or I should say, not just a multiple of half a wavelength, but an odd multiple of half a wavelength. Okay, for constructive, m, 0, 1, 2, and so forth. And then conventionally, for destructive, m starts with 1, and so forth. But you could just as easily have a negative in terms of the math, but it's just conventional to start with m equals 0 for constructive, and m equals 1 for destructive. All right. A classic example that shows interference is what's called Young's two-slit experiment. And this was performed by Thomas Young in 1801. And this, for a long time, was thought to be conclusive proof that light was a wave. And I guess it still kind of is conclusive proof that light was a wave. Later on, about 100 years later, Einstein started talking about the photoelectric effect, and he was claiming that light was a particle. And then, as quantum mechanics was discovered, it's come to light that light behaves like a wave in some ways and behaves like a particle in other ways. But this is a very important experiment because people were arguing about whether light was a wave or a particle, and this experiment seemed to settle it for quite some time, and therefore impacted how everybody thought about light for the next 100 years, and still does. Okay, so the way Young's two-slit experiment works, we all know that I am not great at drawing, so I'm just going to cheat and show you this diagram in the book here. You've got a monochromatic light. It shines through a single slit, and that's the only reason for that is so that the light is coming from almost a point source, and then it goes through these two slits. And as it goes through these two slits, there is a difference when it hits this screen light that has come through this slit to there has a different path length than light that comes from this slit to there. And so we get this interference pattern where there's constructive and destructive interference. Right? So in the midpoint between the two slits, they're in phase, and we hit this bright area. They call them, I don't know why they call them fringes, but the central bright fringe, and that's where there is no path length difference. And then when the path length difference is one wavelength, there's another bright fringe, and then two wavelengths, three wavelengths, etc. And then there's a half wavelength difference. We get this destructive interference, and this dark region shows up. And then 3 halves of a wavelength difference, 5 halves, and so on. Right? So for the bright fringes, or actually before we get to that, let's do some geometry here. If we draw a little picture, so we've got these two slits, and there's light coming in and going off and wherever from various points, and we're making an assumption here, and we're making an assumption that the distance between these two slits, this distance d, is way smaller than L, which would be the distance between the slits and the screen that this pattern is being projected onto. So that if I take the path of a ray from here versus the path of a ray from here, we're making the assumption that these angles are essentially the same, okay? Which is a reasonably good assumption. So let me blow this up a little bit so we can see kind of what that means. So if we're assuming these angles are the same, so as we go here and here, this is theta, this is theta. Our path length difference just comes from if we drop a perpendicular down here, from here on, these are traveling the same distance to get where they're going. And so then our path length difference is right here. And this is d, the distance between our slits. And if this is theta, that means this is also theta. And so this path length difference here is d sine theta. Okay, and that might seem like a pretty significant assumption that these two angles are the same, but in reality, it winds up working out pretty much as though that assumption is true. So this is our d sine theta. So this is our path length difference, because from here on the paths are the same. And if that's our path length difference, that means that constructive interference happens where d sine theta is equal to m lambda. And our destructive interference happens where d sine theta is m minus a half lambda. In this case, m is 0 plus or minus 1 plus or minus 2. In this case, m is 0, or not 0, 1, 2, etc. And then they also put this formula here, m plus a half lambda, m equals -1, -2, etc. Now, algebraically, you could just use this first one and say m equals 0 plus or minus 1 plus or minus 2, etc. But the reason that they number it this way is so that then if you say, I want to find the 10th dark fringe above the middle, then you just use m equals 10. And if I want to find the 5th dark fringe below the middle, you just use m equals -5. You don't have to, shift your index over it all. You just can find it. And that's the same reason they use this. The 0 corresponds to the middle, that central bright fringe, and then you can say, where's the 5th bright fringe above it? And then you just do m equals +5, and so forth. Right. So so positive is above the center, negative is below the center. Now I said that this has to be true, that distance between slits has to be much, much less than L. That is true. In order for interference to occur, that distance has to be greater than the wavelength of the wavelength of the light, because it's less than the wavelength. If it's less than the wavelength of the light, then there can't be a path length difference of a wavelength, and so you can't get any sort of interference pattern. You can't get the constructive interference happening anywhere except in the very middle. So you don't get that that pattern that way. In practice, we want the distance to be about equal to 100 times the wavelength. If that distance gets too big, even if it's still much less than L, if it's too big relative to the wavelength, it becomes very difficult to see the interference pattern because the fringes just start getting way too close together. All right, so we can use that to solve problems. Another way of this question could be asked. You could be asked to find out what angle the light or dark fringes are. You could also be asked to find the distance to a given light or dark fringe. Fringe. And when they're saying this is the distance. This is always going to be the distance from the central bright fringe. Okay, and for that you need to know how far the slits are from the screen. Just doing some quick trig, we can see that the distance from the central right fringe to some point up here, this is L, so tangent of theta would be this distance over L, and so that distance is a y value that is just L tan theta. And so those are the equations you're going to do calculations with for Young's two-slit experiment. Okay. Now, we also can get this interference when waves are reflecting, because reflected waves can change their phase. And I'll talk more about that in the next video.